Hello, everybody. Welcome to your Topic 3 Ticket to Retake. So this was our review that we need to complete to retake our Topic 3 test. So just use this video in any way that helps you out. A little review, reteach, check your answers, all of the above. All right, so first, a couple questions. It says, use the leading coefficient and degree of the polynomial function to determine the end behavior of the graph. So just a reminder what end behavior is. If we think about a graph or a function, what's happening on the ends? What's happening on the right end of your function? What's happening on the left end of your function? And the things that could happen is it could go up on the right side or it could go down on the right side. It could go up on the left side or it could go down on the left side. Now, there's more mathematical ways of expressing that, which we'll go over. But in order to answer that question, all we need to know is the leading coefficient and the degree of the polynomial, and then we can describe what's happening on each end of our function. So number one, here's our polynomial function. We want to check to make sure that it's in standard form. Standard form is the highest exponent first, and then it goes in descending order. So when we're in standard form, then our leading coefficient and degree are both coming out of this leading term right here. So the leading coefficient is a -2, and the degree is a 4. So leading coefficient is the coefficient of your leading term, and the degree is the highest exponent, so in this case, a 4. All right, so the notation that we have to use to describe end behavior. We always want to start out with, and I always start out describing the right side first, because when we describe the left side, it will either be the same as the right or the opposite of the right. So I think it makes the most sense to talk about the right side of your graph or the end behavior on the right side of your function. So the way that we do that is we say if x approaches infinity. Now if I come back over here to this little coordinate plane, x approaching infinity is the right side of your graph. That's where your x's are getting bigger, approaching infinity. So x approaching infinity, we just want to make sure that when we have this, we say, okay, that is the right side of your graph. So what is your function doing on the right side? So then we would say, well, our function, f of x, is approaching either infinity or negative infinity, which means is your function going up or down on the right side? And the thing that determines that is your leading coefficient. If your leading coefficient is positive, then your graph will go up on the right. If the leading coefficient is negative, then our graph will go down on the right. So just to kind of sketch out what's happening in this function, because our leading coefficient is negative, that means that our function will go down on the right side. So if our function is going down, that means that it is approaching a negative infinity. All right, so there's describing the end behavior on the right side of your graph. So the end behavior on the left side, we're going to say if x approaches negative infinity. So again, if I come back here to our x-axis, x approaching negative infinity is the left side of your graph. All of our x values as we head out this way are going to get smaller, 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 heading toward negative infinity. So when you are describing the left side of your behavior, or the left end behavior of your function, the degree is what tells us what's happening on the left side. So your degree is always going to be positive because this is a polynomial. Polynomials have positive exponents. So your degree will either be even or odd. If your degree is even, then it will do the same thing that the right side is doing. So this degree is even, it's going to also go down on the left. If your degree is odd, so if this was an odd number, then it would do the opposite of what the right side did. So if our degree was 5, then I would be going up on the left side to be opposite from the right side. All right, but our degree is even, so our function is going to do the same thing it did on the right side, so that means f of x will approach a negative infinity also. And that's our end behavior right here. All right, number 2, we have our function, and to describe so let's first make sure it's in standard form, 4x squared plus 4x minus 6. So there's our leading term right there. The leading coefficient is equal to 4, and the degree is a 2. So when we describe our end behavior, we always start out with the right side of our graph. So we say as x approaches positive infinity, and the leading coefficient tells us what's happening on the right side. If this is positive, it's going up. If this is negative, it's going down. Because that's positive, that means our function is going up on the right. And when we say that it's going up, that means that our function is approaching a positive infinity. Now, the left side of our graph, we say as x approaches negative infinity, what is our function doing? So the degree tells us what your function is doing. Now remember, if it's odd, it will do the opposite of the right side. So if this was an odd degree, it'd be going down over here. But because it's even, this one is doing the same thing as the right also. So similar to the last one, it is going to approach positive infinity just like the right side of our graph did. And there's our end behavior. All right, so number 3, identify the degree, leading coefficient, and number of terms in the polynomial. So when we do this, we want to rewrite our polynomial in standard form. It's just an easier question to answer in standard form. And if you happen to have any like terms that you can combine, you can go ahead and do that. So standard form, f of x equals, first look for your highest exponent. Highest exponent is this 4, so this is going to be our leading term, negative 2x to the 4th. Now I'm going to look for any x cubed, and we have a minus x cubed. Next would be x squared, so plus 5x squared. Then our x to the first power, minus 2x, and then our constant term, plus 3. All right, now that we have it in standard form, our degree is the highest exponent, which is a 4, right there. Our leading coefficient is the coefficient of the leading term right here, so it's going to be that negative 2. And then the number of terms. So number of terms that our polynomial has, sometimes we have to fill in a 0 term if we're doing some division, but that 0 term is not like one of the terms we would count. So when you're counting up your number of terms, just go by the number of terms that we have written out, not any that we had to add in for a division problem. So our number of terms, 1, 2, 3, 4, 5. All right, number 4 and 5, add or subtract. So subtracting, if you remember we talked about in class, here's where students make the most mistakes. And this had more mistakes than an addition problem on the test. So here's what you got to do. You just need to make this a negative 1 and distribute. Negative 1 times 2x cubed is a negative 2x cubed. Negative 1 times x squared is a negative x squared. Negative 1 times 9 is a negative 9. I'm going to carry down the first polynomial. There's no changes to that one. So 4x cubed plus 2x plus 2x squared minus 8. And then it just goes right in line with when we distributed that negative 1. Now we're going to combine like terms, and we want our answer to be in standard form. So I'm going to find the highest exponent first. We have a 4x cubed that we will combine with a negative 2x cubed. So 4x cubed and negative 2x cubed is a positive 2x cubed. Now we look for any x squared. So here's a positive 2x squared and a negative x squared. So 2x squared minus x squared is a positive 1x squared. Now any x to the first power. So I see this positive 2x and there are no other x's, so we'll just add in plus 2x. And then any constant terms. We've got a negative 8 and a negative 9. We combine those and we get a negative 17. And that's what we get when we subtract. Number 5, this is an addition problem. We do want to make sure we're noticing the operation in between our two polynomials. So when we are adding polynomials, we're just adding like terms. And when you have multiple variables, it's the variable combination that has to be exactly the same for us to add those together. So for example, we have 9 of these a cubed b's. So now I would look and say, do you have any other a cubed b's? And here's an a cubed b. So those are like terms. 9a cubed b. And because it's a positive, we're just combining these as they are. Plus 10a cubed b is 19a cubed b. Remember, when you guys are adding or subtracting, your exponents do not change. If you notice, they did not change on the last one. I didn't mention it, but I just want to make sure I bring that to your attention. Okay, when you have more than one variable in a term and we want standard form is going to order off of the first variable in the alphabet. So because we have A's and B's, we want to order it off of the A's. So this term had an a cubed. After this, I want a term that has an a squared. So as I'm looking through, I see, oh, this one has an a squared. Even though there's a b squared with it, the a squared term, so this whole term would go next. Do we have another a squared, b squared to combine with it? And we do not. So this minus 6a squared, b squared is just going to come down next. Now we want to look for anything that has a to the first power. So here we have a positive 6ab, and that is the only one of those we have. So plus 6ab. And then any constant terms, we have a negative 4 and a negative 6, which give us a negative 10. All right, number 6, multiply the polynomials. You can distribute the 2m, you can distribute the 4. Once I get to trinomials, I personally am a fan of multiplying this out using boxes. I just like the way it organizes my work. So let me show you what this would look like. Because I'm multiplying a binomial times a trinomial, you can see I'm going to have a 2 by 3 box. That binomial is going to go on the side, negative 2m, positive 4. The trinomial will write across the top, 5m squared, negative 4m, positive 2. And then when we do our multiplication, we have these boxes, and so we're just going to multiply. It's using like an area model to do multiplication, so this side times this side would tell us what to fill in here. So when we do the multiplication, we're going to multiply the coefficients. 5 times negative 2 is negative 10. And then m squared times m to the first power, we do add our exponents and we get m to the third. All right, I'm just going to move to the right. We have negative 2m times negative 4m. So the coefficients, negative 2 times negative 4 is positive 8. And m times m, we add our exponents and we get m squared. Now we're going to do negative 2m times a positive 2. So multiply the negative 2 and the 2, we get negative 4, and then the m just stays with it. It didn't change because it wasn't multiplying with any other m's. All right, now let's move to the bottom row. To fill in this box, we're going to do this 5m squared times the 4. So we'll multiply the 5 and the 4 together first, which is 20, and then the m squared didn't change. Now we're going to do negative 4m times 4. Negative 4 times 4 is negative 16, and then the m didn't change. And then for the last box, we have 2 times 4, which is a positive 8. So writing our final answer, we're going to put it in standard form and combine any like terms as we go along. So our highest exponent of everything we multiplied is this m cubed. It does not have any like terms, so that's just going to be a negative 10 m cubed. Then I'm going to look for any m squareds, and I can see we've got two of them right here. So we're just going to combine those, add the coefficients. 20 plus 8 is a positive 28. And because we're adding, the m squared won't change. We're just adding coefficients. So we're just combining like terms. Now we look for m to the first power. We have a negative 4m and a negative 16m. When we combine those, we get a negative 20. And then that constant term of 8 just goes on the n plus 8. All right, number 7, compare the end behavior of the graph of the functions f and g. So we're just going to focus on f of x, which is this one right here, and then we'll do g of x. So our f of x function, maybe I'll highlight it for us here, just so we can see. That's this function right there. So I like us to talk about the right side of our graph first. So as x approaches infinity, so this is the right side of the graph over here, you can see that your function is going up, so that means your function is approaching infinity. As x approaches negative infinity is the left side of our graph. So on the left side of our function, that's going to be this side over here, it's going down, so that is approaching a negative infinity. All right, so for g of x, here's our g of x right here. So as x approaches infinity, the right side of our graph, our y's, which is our function, on the right side is going down, so that approaches a negative infinity. And then as x approaches negative infinity, that's the left side of your graph. What is our graph doing? On the left side, it's also going down. So it is approaching a negative infinity also. When you guys do your end behaviors, this first part, as x approaches infinity, is always the same as x approaches negative infinity. Remember, this is the right side of your graph. This is the left side of your graph. And then we have to figure out what our function is doing. So we're figuring this out on our own. But we always start out with as x approaches infinity, right side of your graph. As x approaches negative infinity, left side of your graph.